Perfect. Okay, so let me just start with a spiel as to why I decided to do the talk, and let me also say that when I created this talk, I did use AI tools, right? So I hope the irony is not lost on you, even though I'm going back to the fundamental. I am using AI tools when creating this talk as well, right? So it's not entirely me, right? So it's plenty of AI tools. I'm not asking you to bet against AI, right? That is not what I'm asking you to do here. I'm going to be using a lot of maths in this, right? So if that's not what you expected here, I do apologize, right? So I'm sorry in advance. We're going to be doing a lot of linear algebra stuff. Did I foresee any of this LLM stuff coming? No, I did not, right? So I think Eugene is being quite generous in his description over here. Look, my fundamental passion is maths, right? Like I love maths more than anything, and that's really why I got attracted to the space. And you'll probably see some of that bubbling up when I give this talk. So when it comes to Bayesian stuff, the reason I got attracted to that is because there's maths in there. There's some differentiation stuff. There's some pretty cool stuff in there that I just naturally got drawn into. It just so happens that LLMs happen to have that stuff from a while ago, right? So, like and the other thing that happened was that, so for the past, like, so I've been working, I've been working at REA, and I've been interviewing for the past 6 months. I've managed to get a job recently, but like I'm starting to see this trend where everyone is always talking about AI, right? Like the most recent thing is MCP. I have no idea what the fuck MCP is, nor do I care, right? Like I don't. It's just like it's yes, LLM is this amazing tool, but what I'm seeing is this degradation of science as a discipline, right? So and really makes me sad that this like even when it comes to AI engineering, I'm really seeing a lack of engineering, right? So yes, prompt engineering, there's plenty of engineering left to do, right? So there's plenty of guardrails left to do. Like there's plenty of tests left to be done. Everyone is rushing in the prompting side, right? Not really caring about what needs to be done in that space. When it comes to machine learning, there's still a science to be done, right? So it is very possible. I'm just being a grumpy old man, just shouting at the cloud, right? It's very possible, right? Like, right? So I will give you that. But yeah. So today I just want to focus a little bit on the fundamentals of how do we build a large language model, less so about the hype stuff, right? So less so on the acronym stuff, right? So again, not saying that there is I'm not debating about AGI or any of the hype stuff. I understand that there's plenty of value over there. Just talking about how do we build to the point that these things are, right? So the things that we're going to be talking about, we're going to be talking about tokenization, right? How do we build up like the very fundamental thing, like what is the word within a large language model? We're going to talk about attention, right? So like how do these, we'll get that. I didn't have time to do the training the loss function bit, but we will talk about like how do we train up these models. Chat templates and supervised fine tuning. That's really the second stage, and the last piece of the puzzle is reinforcement learning. I'll talk about a specific version of reinforcement learning, right? I won't talk about all these possible versions of reinforcement learning because it has gone through two iterations of it. Okay. Now, before we jump into tokenization, I want to talk about this paper back in 2013 called Word2Vec. So the Word2Vec, I think, like for me personally, this is probably the thing that really sparked this whole LLM revolution. So what happened was they started off with words, right? So the initial version of tokens, if you will, and they put it into higher dimensions. And the trend that they found was that when you look at the differences between words, so for example, if I look at the differences between king and queen, it was roughly, not exactly, but roughly the same difference between man to woman as king to queen. You get walking to walked, was swimming to swam, right? The same thing appeared with country capitals, right? So Spain to Madrid, Italy to Rome, and so on, right? So you start to notice these word associations, right? Now, keep in mind back then, back in 2013, we didn't have all these, well, they had some GPUs and they were starting to train on GPUs. But the data set that they trained on was simply Wikipedia, and that was it, right? So relatively, this was still a small data set, but it was starting to see these trends, if you will, and it was not good enough at the time. Okay, so how do we train these models? Right. Now, I'm not going to go through the exact algorithm, but let me jump into a tiny bit of maths because that's what we're going to be doing a little bit more of in a second. So, I could turn this on. Okay, so suppose you have this sentence where you have the cat sat on the mat, right? And what we're going to do is we're going to focus on a window of 5, like, so this set of 5 words, right? And we're going to choose the word, like the middle. So we're going to focus on the middle word sat, right? And we're going to randomly choose a word around it, right? So in this case, cat. Right? So suppose it randomly chose that word cat, right? So I know it's a little bit convenient, but let's just say we chose that one, right? So what we're going to do is we're going to try and maximize the word, okay, I'm jumping ahead a bit, but the vector association of cat with sat, we're going to try and maximize it. And we're going to try and minimize sat with a random word mug. Okay, so suppose I had the extra word mug in my vocabulary. Okay. I'm going to try and minimize it. So let me step back for a second. All right, let me start again. So when we initialize the vectors, every single one of these words will get a vector, right? So they are all completely randomly initialized, right? So will get, say, -0.1, 0.1, and 0.5. They all have to be the same number of dimensions. Cat will get, again, the same number of dimensions, but different number of words because it's getting randomly initialized. And then we're going to get, like, every single one of these words will get vectors, right? Including, say, suppose I had mug somewhere in this vocabulary, right? And then mug is somewhere going to be there, and then get that. Okay, so what we're going to do is we're going to get a word. So sat, and we're going to try and maximize sat and the what do you call this? The dot product of sat with cat. And we're going to try and minimize. We're going to try and minimize sat with mug. Does that make sense? Because we want, like, if we look at a if I look at this on a grid, what I want to do, like a cat will be associated with sitting, right? So that the vectors cat and sat, you just assume that they will be similar, right? The angle, at least, you want them to be minimized. And then cat, well, not cat, but sat, at least, you don't want them to be very far away from each other. Now, I am skipping a whole bunch of detail over here. Like, for example, these are normalized vectors, so you can't, like, one way of cheating way of doing this is to expand, like, just to increase the length of this, right? So they have a restriction of the unit length. So you can't keep increasing the vector. So there are limits, but that's roughly the idea, right? Now, obviously, there's a single sentence, but when you do it on Wikipedia scale, you get all these associations, right? So when I come back to, you're not seeing any of this, are you? Right, sorry. Sorry, okay, so that's what I was showing. So what I was showing was that the angle between cat and sat, I want to try and minimize, and so sat and mug, for example, I want to maximize, right? So when you yeah, Wikipedia scale, this will learn a useful embedding, right? Again, so coming back to this example, you get all these associations. Does that make sense? Yeah. So this is the initial way of training. It was a bit more complicated than what I had mentioned, where they chose one word at a time, but roughly that is the idea, right? The reason I don't want to get into it too much detail is because we're going to get into large language models where we have a lot more nuances. Okay, so we'll keep moving. But the main idea that I want you to understand is that this thing in large language models is called an embedding. Right, so instead of saying a vector, we call it embedding large language model land. Okay, let's take a tiny bit of a break and let's talk about tokenizing let's talk about tokenizing. Right. So in that example, tokenizing was just a word at a time. Right, it's a simple word. You just look at spaces and you break it up into a word. Right. Now that doesn't work when it comes to large language models, because if you notice, large language models these days can deal with multiple languages as well, right? They can actually deal with emojis, images, whole bunch of things, right? So the way that you need to do with that is that you need to be able to break it down to a single byte as well, right? So to deal with a concrete example, suppose you have a vocabulary that has this, right? So it has hug 10 times, pug 5 times, punt 12, and so, etc. Right? So that's a vocabulary. So if we're going to do a encoding of this, if we're going to build a tokenizer for this, the way that we start off doing this is that we will break it up into individual letters. So that's your first step, right? So you get D, G, H, blah, blah, blah. And then the first thing that you do is that you look for 2 letters at a time. What's the most frequent 2 letters in here, right? So you go, is it HU, UG, blah, blah, blah. So you find out that UG, so UG you have 10 times. The next one, UG, so 10 here, 15 from here. So UN becomes, there's 12 of them, 16 of them. So UG, you end up getting 20 times when you add it up across all these words, right? So UG is the next thing, that the next most frequent thing. So it gets added up onto this thing. By the way, can everyone see at the back? Do you want me to zoom in? No? Okay, let me zoom in. Correct. So just looking at this, in terms of the 2-letter ones, UG is the most frequent 2-letter ones compared to UN. It's more frequent, right? But you'll notice that UN is the next more frequent one, so you add that in the next step, right? But every time you add UG, like you combine them together, and then you look for what's the next most frequent one, and then you keep combining them, and you keep searching. So basically, you're going to keep expanding the vocabulary until you use up your vocabulary budget. By the way, feel free to ask questions during this. I'd rather you ask questions early as opposed to keeping them till the end. Any questions? Yeah.
I don't see any sequencing in there, because how would it know the sequencing matters for
Sequencing. Yeah.
like in this case, you're just considering words as individuals. But
Yeah.
obviously in a text, they're all in a sequence. So how would it understand the sequence?
Sequence of words, you mean?
For example, 10 times, 5 times of those. but
Yeah.
you broke it down in a bunch of a paragraph. You must have gotten that.
Yeah. So you do break it. Okay. So there are different versions of so this byte pair encoding, right? So there are different versions called sentence pair encoding and so on. But we're specifically looking at this one, which is used in up until GPT-4 at least. This is what was used. But this one looks at word boundaries, and that's where it stops, right? So it's okay. You want to expand your vocabulary as big as possible, right? Because keep in mind the other thing that you want is if you remember LLMs, when you're calling an API, they charge you per token, right? So if I charge you, if a vocabulary was just letters, that would be a very expensive LLM, right? So you want your vocabulary to be as big as possible, right? So I mean, there was a question the last time that I presented that, so why don't you just expand it to infinity? There's a cost there as well, because like each of these vocabulary you find, like in the next one I'm just about to show you, will have an associated embedding as well, right? So there's a cost in terms of storage as well, right? So there is a give and take with this tokenization issue, right? So the bigger the vocabulary, yes, it's great. So you might. So what you said about expanding this thing, you might get to a point where you expand beyond the space and start combining words as well. So that is a possibility. This is by pair encoding. I'm not entirely sure how that'll work, but it's possible, right? Yeah, but definitely you generally want a bigger one. Did I answer your question?
Partially, maybe in the next few slides, I might get.
Okay. All right. Any other questions?
Sorry. I know that this is a very popular tokenizer method, but I know that some data scientists directly use one-hot encoder. Yeah. So will this, if I choose one-hot encoder or byte pair encoder, will it affect the final performance of the language model?
So the one-hot encoding is equivalent to one-hot encoding is equivalent to 100 encode is not used at all, right? So anyway, because so what happens with tokenization? Tokenization is a way of building a dictionary to say this is going. So sorry, looking at this vocabulary. So for example, B will be 0, G will be 1, H will be 2, and so on, right? Where the one-hot encoding, so how long is this? Say it's 10, pretend it's 10. The one-hot encoding thing will come into play when this will be 1, 0, 0, 0. The next one will be 0, 1, 0, 0, 0. So it's equivalent, right? So you can translate between one from the other, right? There's the one-hot encoding is like a backend, like it's a, you don't need it anymore, right? So it is happening automatically. Is that okay? Yeah, the one-hot encoding is a mathematical concept, right? It's already happening, right? It's just not necessary to. It's not necessary to code it up. I'll draw it up later, right? Like yeah.
Yes, probably not essential directly for the audience, but I would be curious how more expensive would be the English language as analytic language. You know, there's so many variations compared to say Chinese, which is and it's like more precise. So I don't need as many sort of like tokenization, and would be more precise in terms of predicting the.
I don't know how to answer that question directly, but I've seen that some. So a big complaint that I've seen is that with non-English languages, people end up using up more tokens, right? Because of this problem, because most of the LLMs get trained on English language, and the vocabulary that gets built up is on English, unfortunately, right? So it ends up using up these single tokens, and it ends up being an expensive call to the LLM, right? So that is definitely a known problem, right? So
the more tokens, it will be more precise and will not cost in terms of.
no. So they're more, that ends up taking more. It ends up, because it's at a byte level, it ends up taking more tokens to build up that single token that you're talking, single character you're talking about, right? So it's not what you're after, right? So to build up a single Chinese character, it ends up using up more tokens, right? Even though it's a single Chinese character, it uses up more tokens, right? Just because it's a single character doesn't mean it has the vocabulary in here, right? So yes, it'll be great if it's in there. If it's in there, that's great. But what I'm saying is it's usually, it might be the case that it won't be in there. So it's more of a training data problem.
Maybe using a wrong approach, because if you're applying the English language model to Chinese, obviously it's a wrong approach.
Yeah.
Wanted to
Let's let me keep going, because I'm
everything.
conscious of the time.
Okay.
What time do you have till, Eugene?
Oh, look, if you don't want to answer questions, you can keep going till 7:30.
Till
If you want to
7:30?
answer questions, keep
Right.
going till 7.
No, let's okay. All right. Okay. All right. So
Currently 6:30.
yeah. Okay. So so the next thing that happened, right? So was Andre Kapati. So he's the director, or used to be the director of Tesla. I think he worked for OpenAI for a bit as well. He came up with this amazing blog called The Unreasonable Effect of RNNs, right? So and what he tried to do was to predict a single character at a time and just regurgitate characters, right? So in this case, I'm trying to get the words hello, right? So H try and predict E, E predict L, and so on, right? So this is using a simple RNN, right? So I don't think he even used the LSTM back in the day. And yeah, he got it to work, right? So, and I just want to show the results before. I'm not going to get into RNNs in this one, because I want to jump straight into attention mechanisms, because that in itself is a pretty big piece. But the results that he got were quite amazing. So the Shakespeare, so this is he trained them on just all of Shakespeare's work, and this is the results that he got, right? So if you were to try and Google this, you will not, like, this work doesn't exist anywhere, right? This is not Shakespeare, but you can see the grammatical structure is very similar to something that Shakespeare would write, right? So it's very convincing. He also got a whole bunch of LaTeX papers on archive and trained it on that, and he got it to compile, right? So compile. Don't try and read the maths. It's all bullshit, right? So it's nothing, right? So, but the point is that it compiled, right? Like it looks like it's maths, right? So it's something, right? So this is back in 2015, just running on his own laptop. So impressive stuff, right? So for back in 2015 for training a couple of days, and also using just bare bones RNNs. Yeah. So I think this is probably the foundations of using large language models and what's possible, right? So again, not using the entire internet, just basic stuff, right? Now we start diving a little bit deeper, right? So now we get to the point where we start using, so attention is all you need, right? So this paper came out. Can't remember what year this is, but I think this is really where things start to change, right? So this image is from Jay Alma's blog post. So I just want to read this sentence. So the sentence says, the animal didn't cross the street because it was too tired. Right? Now, it, as a human, we know that it is referring to the animal, right? But to a machine, how do we know that it is talking about animal and not the street, right? It's a valid question, right? That it could refer to the street as well, right? So let's dive into how that all of that happens, right? So this is where I'm going to jump into a bit more, a bit more maths. Okay, so feel free to ask questions. By the way, this is where things will get a little bit more interesting. So in this example, what I'm going to have is I have two sentences: the cat sat on the mat, and the dog barked at the mailman. I have very specifically made both the sentences six words on purpose, right? Just to keep it simple. Usually you don't get that. You have different varying lengths, but we're not going to deal with that, right? We're just going to keep it simple. And the first thing that I want to do is we want to machines can't deal with words. They need to be converted into. We need to tokenize them. We're not dealing with white pair encoding. We're going to convert words into indices. So we're going to get this dictionary, right? So we get this index to word, right? So 0 index because it's Python, and then you get 0 is at, and so on. Everyone with me so far? Yeah, cool. All right. So and then we're going to convert these two sentences. We're going to convert them into X, right? Because we're going to shove this into a transform model, right? And then we're going to convert these into embeddings. So remember what I spoke about embeddings before, right? So every single one of these words is going to get an embedding. You can think of it as a lookup table, right? So this lookup table, we're going to randomly initialize it. I picked this number out of thin air, right? So I'm going to have so each of these 9 words going to have dimension of 5, right? It can be 2, it can be 3. Generally speaking, we're talking about thousands when it comes to large language models, but for this example, we're going to choose 5. That's what we're going to have. And what we're going to do is, so these batch size of 2 by 6, right? So six words again. We're going to convert it to, we're going to convert each of these sentences to an embedding. We end up with 2 by 6 by 5. Does this bit make sense? Because I think this, like, if you're not following me up here, I want you to let me know. This bit is important. Yeah.
Well, those numbers 1.9, they're just randomly generated.
Randomly initialized. Okay, we're going to like I'm not going to show you I don't have time to do the training bit, but they're randomly initialized, right? So they're going to mean something useful in the end, but for now they're completely useless. Does that help? It's
you're creating a vector so that the computer can recognize words as numbers, essentially.
yeah, absolutely. Yeah.
You train the vector when you use training, you specify or I don't know, train those numbers so that they're not random anymore. They're trained numbers so that they can actually recognize which words are closer to them.
Yeah. So the number. Yeah. So once they So all training, all models when they start off mean absolutely nothing, right? So even your linear models, right? Like even if you're talking about y equals xw, right? Is the w when you start off means nothing, right? At the very beginning, it's just after you train with your error bars, like after training with stochastic gradient descent or your OLS or whatever it is, after you train it, in the end, it means something, right? It's just like at the beginning, you need to start somewhere, and we're starting off somewhere.
So it's basically a dart on a dart to start with.
It's basically
A dart. Throw a dart on a dart.
It's a dart, exactly. Yeah.
And then you work out whether or not the dart in the future was where you wanted to throw it, or you
Correct.
throw it somewhere else on the dartboard.
you don't start. So once you start, you keep going, right? You use the data to keep iterating, right? So yeah, you do use gradients to keep going the direction that you need. Yeah. So yeah.
Work out the relationships between all of the various things.
That's right. Yeah. So unfortunately, I haven't had time to do the gradient side of things today, right? So I do apologize about that. But yeah, great question. Yeah. Any?
Does the dimension size must be smaller than the dictionary size?
Dimensions? Which dimensions? Oh, you
Within
mean the
Y, right?
No. So that is coincidence, right? So I could have. Okay,
You're choosing
good.
something larger than that. Will it converge?
Good question. Okay, so are you coming from this maths or statistics background?
I'm from control background, so relevant.
Sure. Okay. So this was okay. So this was actually something that I struggled with. Because like I had this question back in the day. So yeah, very good question. No, I can push this dimension size up to thousands, right? And will it converge? It will converge up to a. I don't know what the right word is here, but it will give me an answer, right? So it's because the gradients still exist, right? But yes, you're right that there are equivalent answers. There are infinite answers, right? It gives me a useful answer. Is probably a better way of putting it, right? Yeah.
Yeah, just on that question, I think you can, but like in the extreme case, you will have one hot encoding, which is using the vocabulary size, right? Dimension is equal to the vocabulary size.
The one hot encoding is not relevant over here.
Yeah, no, I'm just saying in extreme case. But if you say that the dimensionality is greater than the vocabulary size, my view is that there might be some redundancies.
The dimensionality is, there's plenty of redundancies. Absolutely, yes, absolutely, yeah, yeah. So, in fact, with all these billions of billion parameter models, most of the no, okay, with the billion parameter models, it really doesn't matter because the amount of data that's coming in is extremely large as well. So I suppose it doesn't matter in those cases. Look, there are also other tricks where you can regularize them. So it can become a proper problem. If you're coming from a maths background, you can regularize this and make it a fully formed problem, right? So it doesn't matter, but you get a useful answer. This is my fun answer. Let's keep going. Any other questions? But very good questions. I love this. All right, let's keep going. All right. So the issue with the previous paper with Bert to Beck was that they only looked at the word on itself, right? So they didn't look at the context of the question. So for example, if I talk about bank, I think the first thing that comes to your mind is like financial bank, right? So if I say river bank, you straight away switch to a different kind of bank, right? The context matters, right? So the question is, how do I take into account the words around it, right? So the attention mechanism is how you do it. So the way that we do this is that we are going to create this attention matrix, and I'll show you how to do that, right? So we're going to, the first thing that we do is that we're going to multiply the embedding with these three things, these weight matrices, or the query weight matrix, query key value weight matrices, right? So these two things are learnable, right? And we're going to multiply them and get the query key value, right? So these ones, again, the shapes as dimension by dimension. So the embedded thing that's coming in is batch size by sequence and by dimension. The output is also, again, batch size by sequence and by dimension, right? So I haven't changed, like dimension-wise, I haven't changed anything, right? So nothing's happened so far, yeah? But the next bit, I'm going to multiply the query by the key transposed. At this point, the shape becomes batch size by sequence and by sequence. Right, so now if you remember your matrix algebra, this the sequence, so yes, sorry, everyone. The dimensions cancel out the dimensions, so you end up with a sequence length plus sequence length. Right, so this is the important bit. Right, and then you do this softmax operation to make it a probability thing, right? So just very quickly, if you've forgotten what a softmax is, let me just very quickly show you softmax. That's what the softmax is, right? So you get a bunch of numbers, and it can be positive or negative, right? And then you end up on the other side a bunch of positive numbers, but they also add up to 1. Right? So that's the main importance of them, right? So again, like it's the exponentiation makes them positive. It's a division by the sum of them makes them sum up to 1. So so the shape is the batch size by sequence length, right? So 2 by 6 by 6, right? So remember 6 words. Yep.
Can you give an intuition like you did for word 2-week, where you're trying to separate cat and mark, but you're trying to get cat and sat closer? What's the intuition behind key value query?
The key, okay, so forget about the key value query. I think that's probably coming from a more of a computer science side where you have the caching stuff and a whole bunch of things, right? So forget about that if you don't recognize key value stuff, right? This is more how do we get the context? How do we get the context of all these? How do we get a signal from all the surrounding words?
Enhance the current word.
To enhance the current word, right? So how do we manipulate? So far, I need a way of getting signals from the surrounding words. So I need a way of getting this attention matrix, right? So forget about the softmax even, right? So I need a way of getting signals from. You do need query and key. I need a way of multiplying something from a surrounding neighbors, right? That's why I do. So once I have this query and key, I have to transpose them, right? So the batch size by sequence, and it's the fact that I need this sequence by sequence. This is the main bit, right? That's how I get signal from my neighbors, right? So once I have that, I have this final step where I go attention times value, right? So with this one, I end up with batch size by sequence by dimension. So I'm back to my original dimensions, right? So I get my neighbors, signals as well.
Is it just because of that computer science-based background that attention introduces that you do query transpose to key rather than value and then multiplies to key? Is it coming from the comp sci background where obviously for a query, you're querying a key, then you get a value? Is that how that works? Or?
No, don't read into the query and the key and the values. Don't read into that.
Can I do query times value first?
You can. Yes.
Okay.
Yeah. So you can with all these things, you can definitely, yes. So you can switch those namings around, definitely, right? So that's more, the query key value, again, that's more the computer science naming convention, right? So don't read into it too much, right? But good question. Any other question?
If we zoom back 1 step, what does it really attention do in this particular case, and what you try to capture or means anything in terms of the part of the algorithms and what the inventors are trying to achieve around here?
What are they trying to do with it?
Yeah.
So the original thing that they're trying to do is, it's a good question. So is this, right? So it's that they're trying to get when they're talking about it, right? So the embedding of it needs to be talking about the animal over here.
Right.
And so that's the ultimate goal.
The relationship between that word to the other part.
To the other part of the sentence. So that's the ultimate goal.
What does it mean? The relationship meaning, it's the word that close to the other, or what's the meaning of, the relationship from that word to the other?
So once you get to the output of it, like all of these are just like they're all just mixed. You don't get this nice word names. They're gone out the window, right? So you can forget about that, right? So you don't get this nice diagrams anymore, right? So you don't get this nice geometrical stuff anymore. Unfortunately, all of that is lost, right? So yeah. Let me keep moving, right? So because we probably let me keep moving, right? So that is the attention mechanism. There's a few things that I'm going to skip over just for sake of time. So the two things that I'm skipping over is the fact that when it comes to LLMs, you're not allowed to pay attention to the word in front. Because remember, the word, when you're generating words, is one word at a time, right? You're not allowed to pay attention to the word in front of you. And the second thing that I haven't spoken about is this thing called positional encoding, right? So with attention, not so much attention, but with transform architectures, you need a way to differentiate between which one is word one, which one is word two, right? So when it, let me come back to this diagram. So in this diagram, it was very easy to differentiate between word one and word two because there was a nice signal coming in from the previous word, right? Whereas with transformers, like every single signal is coming from everywhere, right? So you don't know which one is which, and the only way to differentiate is to have a separate embedding. But anyway, we're going to skip all that. Look, I know this is a lot, right? I can't, and some of you are probably going, what the fuck is this, right? And that is okay, right? The goal of this talk for me personally is more that I want to get you curious, right? I want to get you curious to the point that you're going to go home and just look up a bunch of this stuff, right? For me, like I'm doing this talk because I'm just, again, coming back to my original point, I'm just seeing a decay of just everyone just prompting everything, right? So it's just I want everyone to go back to the basics and just at least be curious about a bunch of things so that you can just start reading up stuff, right? So I don't mind that you don't understand. I just want you to, I just really want you to be curious, right? So it's okay that you don't understand everything. I want you to just be curious, right? So that's all. That if I've gotten you curious, I think I've won. So I'll take that, right? So let me keep going. All right. So I promise you, I do have a reason that I have this meme. So these days, the way that you train LLMs is to shove the entire internet through it, right? So the first stage is to train a model so that you it's not Wikipedia anymore, right? It is literally the entire internet, the entire open internet, right? So you do need to clean the data, right? And once you clean the data, so you do things like get rid of HTML, right? So because you want to look at words, not HTML tags. But so once you do that, has anyone with ChatGPT just shoved their, when you get like a Python error or any kind of error, just shove the error in without asking a question and got an answer back? Yeah. And do you know why you get an answer back as opposed to, say, not just completing the rest of the error? So for example, if I just copy and pasted just a snippet of that error and say, oh, value error, blah, 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 do you know why it doesn't just complete the rest of that error? Because keep in mind, LLMs are just completing tokens, right? Any
provides fine tuning of the conversation turns between.
It's was fine tuning, right? So this is the second stage of the LLM training, right? So the first stage is just a single token at a time. You take the internet data, just train a model like just train as it is, like a single token at a time. The second stage is that you do this, right? So you go, you have a system prompt and then you have a user prompt, whatever it is. So you're a friendly chatbot who responds or in this case, this is not quite valid, but you are a useful assistant. And then you go, here's my question, I have this error. And then you have another thing called assistant, and then you would have what the valid answer is, right? So in the early OpenAI days, the reason that they jumped ahead of all the competition is because they had a very good data set that they created with these messages, right? So they had a good system prompt, a good user prompt, and a good assistant prompt where they manually curated this data set, and then they created this supervised fine-tune set, right? And then they trained on this one. So that this is a second stage of training, right? So without it, without this, they would just keep on completing the error, right? Because it doesn't know what you're supposed to do, right? It becomes useful with the supervised fine-tuning, right? So it's not enough to just complete the token, right? This is the only way where you get a compressed understanding of the world, if you will, right? So this is the second stage. Now, before I move on, let me skip back to, I want to do one other thing, and that's on the inference. So on the inference side, right? So in this case, I'm using the Quen model. I'm saying you are a physicist. Well, what is the distance from the Earth to the Sun, right? So I have the system messaging you are a physicist, and the question, user question, I wanted to generate an answer, right? So the usual way that you do it is just go model.generate, and yeah, so in this case, the average, it is a bit verbose, right? So and that's probably because I'm using a fairly small model, 3D model, and the average is from the sun is blah, 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 and it gets the answer eventually. No, it doesn't. Okay. Yeah, so okay, so it's clearly taking a while. Yeah, it would have gone to the answer eventually, right? But if I was to do this manually, right? So if I was to do this manually, the way that you do this to generate an answer is like this, right? So I'm not going to go through this one by one, but what you do is you get the inputs. So you start off with the inputs. You generate a single output. So in this case, I'm probably running out of time, but when you do model, let me start again. So the inputs over here is the question that I had over here. What is the distance from the Earth to the Sun, right? So tokenized version of it. And then when I push this in here, the output load list that I get is a batch size of 1, and the entire vocabulary size. The vocabulary size could be something in the order of 50,000 tokens, right? And then I need to take the probabilities, right? So remember, the way that you get probabilities is I need to do softmax, right? Forget about the temperature, right? So temperature it's about, just assume temperature is 1, right? But then we randomly sample. Instead of taking the absolute maximum value, we randomly sample one of those tokens, right? And the reason that we do that is that it turns out that if we take the maximum token, it will keep on looping. It will keep on loop. It turns out that it loops through the. It gets to the habit of looping through the answer, right? But anyway, so the next token ID is what we get, and then we append it to what we have so far, and then we're going to loop through that again. Okay, so we get this, put it into the model again, and we're going to keep on looping through that again and again until a maximum number of tokens is generated. All right, so that's how we generate tokens, right? And then we decode the answer at the end, right? This is not the only way of getting tokens. There are plenty of other fancy ways, but this is one way. Any questions about how we do inference? Yeah.
What if I don't want the output maximum number of tokens? I just want the output to stop when at the answer.
Yeah. So when it has the answer, I mean, when it has the answer, how do you know when it has the answer? So this is where prompting stuff comes in, right? So that's the unfortunate thing. So look, there is this thing as well, right? So I have this other breaking condition where it says when the end of sentence ID is seen, it does end, right? So it's either when maximum number of tokens is reached or when the end of sentence ID is seen, right? So there is a second condition. But yeah, good question, right? So you can have prompt on this, so plenty of other things to do as well. So absolutely, right? Yeah. Any other questions? Okay, so the reason that I brought this up is because I want to jump to the last piece of the puzzle, which is on the reinforcement learning side. So, okay, so the last piece of the puzzle is the reinforcement learning with human feedback. Okay, so I specifically want to talk about the GRPO algorithm. Can't remember what it stands for, but okay. So in the initial stages of reinforcement learning with human feedback, there was actual human feedback, right? So, but the last I can't remember if it was DeepSeek or I think it was DeepSeek. DeepSeek math, yeah. So the paper did not. I don't think they used any human feedback at all. They used this algorithm called GRPO, right? So, and the reason that they could use it is that they found some problems like maths and computer science. You can just put the answer back into a computer to right, so like a math solver. You can get it to the math solver can do it. Computer science, you can just go Python or Python .eval. I can't remember the command, but you can get it to evaluate the answer, right? So you can generate an answer and get the computer to check if it's valid answer or not. And the reason I showed you that the way of generating all those things is because you can generate multiple answers for any given question, right? Because anytime I'm randomly sampling, every single time I generate an answer, I can generate a completely different answer, right? With high probability, I can say that like every single time they're going to be different answers, right? Because they're the probabilities that we're dealing with, right? So what you do is the reward can be, did I get a valid output or not? And then I'm going to for every single question, what is the mean? What is the divided by standard deviation? It's the mean is yes or no, could be yes or no, could be something else. Normalize it, and I can't even remember what I've done over here. So you compare it to your initial set of weights, right? Now, when you're doing this, you do have to start off with a good model, right? So it can't be, it has to be the previous version of DeepSeek or something like that. So you need to keep comparing to the old version. So that's where this KL divergence, all these things come in. But point is, you keep improving on the old version, and so you have this iterative loop of the model improving on itself without having a human in the loop. Right? So this is the last step of the model that keeps on improving. And so this is the last piece of the pie. So anyway, that's it. I know that was a lot. So let me just end it over there. So, yeah. Wait.
Sorry, I usually in the reinforcement learning paper, I usually saw that there are reference policy and policy, reference model and model. So what's the difference between like reference something or something else?
What is the difference between the reference and the?
For example, there is a reference policy here, and usually there are policy and reference policy. So what's the difference between that?
Yeah. So reference policy is the reference model. It's the same thing, right? So reference model would be the same, the initial model that I start off with, for example, right? So the previous iteration of DeepSeek, for example, and the what's initial policy? Okay, good question. I don't know. I don't know why I wrote that down. But yeah, good question. So yeah.
Thank you.
I'm not entirely sure whether we need to use the microphone for questions. Probably a good idea. All right, let's have some hands. Let's have some questions.
Hello, thanks for the talk. Just a simple question about the supervised fine tuning and ChatGPT. Like, is there just one foundational fine tuned model behind ChatGPT, or are there like multiple models and then something that chooses and just delegates to the relevant model?
I'm fairly confident there's only ever one, because the whole point of all these foundation models is to have a single model that does everything. Right. So what you generally want is to have a variety of data points that can train as much human knowledge as possible, and then just bring it into one thing. So hence the word foundation model it's a foundation of human knowledge. So
like in that case, you said like, when we just put the error logs, it's not like generating more error logs, but just actually solving the problem. But how does it actually know if I really want just more error logs or like actually solve the problem?
So the supervised fine tuning is what differentiates it between generate more error logs.
Right, but like, how does it actually decide which one I want?
Which one?
Like, I may just want it to generate more error logs. Is this like a heuristic decision they made, or people would drop one?
So okay, let me jump back to this thing, right? So maybe this is probably a bad system message that I have, but general system message would say you are a useful assistant, and then the user content would say, here is the error logs, give me a valid answer, right? And then we would paste the error logs, and then the third one will be assistant and then the content. Right. So you'll be training on that.
Like, let's say I'm a crazy guy. I don't want it to solve my problem. I just want it to generate more logs. How does
that will not happen. So if you do that on ChatGPT, it would give you an answer, right? It would not generate more error logs unless you very specifically specify that at the top and say generate more error logs of the same.
Okay.
Yes, I have. Thank you for the talk, by the way. I have a question. We have, to my knowledge, at least 3 ways we can, change the response of LLM. Basically, by training the base model, and by supervised learning, and by prompt engineering. Right? If I use multiple shots to kind of teach the LLM a certain behavior. What are the actual differences between the 3? I mean, are they equivalent or?
So
for example, in the supervised learning, we have those QA books where we use this QA thing to further fine tune it. If I put this QA book as part of the base model training, will it work the same way, or?
I'm not following. So you mentioned 3 ways. So one is to prompt engineer. The other one is to fine tune. What's the third way?
Okay, forget about the prompt engineer. Just think of the base model training where we just train it with data corpus, right?
Yeah.
And then we have supervised fine tuning where we have this QA questions and answer pairs.
Yeah.
If I collect all the QAs that I will use in the supervised fine tuning, put them into the base model training as part of the data corpus, will I get something similar? We'll get exactly the same model or similar model as it compared to I trained it in a 2-stage.
Okay, so these days generally what you do is that you do this thing called LoRa training, right? So you train the model to do what you want, right? So you take an existing model off the shelf, you don't add it to the base trains thing, because like, keep in mind when you add it to the base data set, you kind of dilute your data set among all these other stuff, right? Because you only get a few, like less than an epoch of training on this specific thing, right? If you want your model to do what you want, you would very specifically train it like a few epochs specifically on only your data set. And the way to do that is that you just go take off the off-the-shelf model and do LoRa training. LoRa training is that you roughly is this. It's not training a few weights. It's kind of anyway, it's a quick way of training the model, right? It's a quick way of training the model, but that way you will only generate answers to your specific data set, right? So that way you don't get this issue of dilution.
It's more of a better practice.
It's definitely better practice to lower training. Yes. Yes.
Thank you.
Do you know how, like ChatGPT, Gemini, those, if they actually look at what your prompt is to decide what role to play, if they have some kind of like slick logic behind that, or is that baked in the foundation model? You know, like if you give it like a programming question, it gives you an answer to a programming question. But if you ask it for a recipe for dinner, it gives you something, and like that's a different role altogether to play. Do you know?
I don't think it. Look, the models have been getting bigger and bigger, right? So I don't think it's changing. I don't think it's changing the role, right? So I don't think it's dynamically adding the prompt every time you type in something. I'm 99% sure that it's not doing that. I just honestly think that that's good enough to the models that are just that good enough to be able to give you an answer. So I think Jeremy Howard gave a good answer. Like when LLMs came out, there were two camps. Like one just said LLMs are just stochastic parrots. They're not really giving out anything useful. But there was another camp where they genuinely believed that they had a really good compressed understanding of the world, right? So I'm on the other side of the camp where I believe that LLMs do have a compressed understanding of the world. So for me, they don't need to have this extra prompt to tell it that, okay, you need to switch roles to go into this route. Sure, it will help, but do you need it? I highly doubt that you need that. So especially with the commercial things like ChatGPT, where it's an extremely large thing. And so it's like small 3D models, like what I'm showing you. Yeah, sure, that'll definitely help. But for anything like 100B plus, no, I don't think you need to. But yeah, thank you.
No more hands. All right. No more questions.
So previously I was in a lecture where we did a bit of a test on language, and we put in a question in French and it responded in Spanish as an output. And that was surprising that it didn't respond back in French or in English. It chose Spanish, and I just wondered if you had it. And the response was that it got one of the nouns wrong. It wasn't masculine, it was feminine. I made the answer actually grammatically completely incorrect. Yeah. So do you have any sort of insights into that sort of logic that it's trying to do?
What it's trying to do over there.
Why did it choose one language over another? And
I don't, to be honest. So this stuff again is jumping into the prompting side of things. I don't know. But I'll be very surprised if I'm assuming this would, like I remember hearing about this. I'm assuming this will be about two years old now by now. I'll be very surprised if they haven't fixed that issue by now. So like people, as soon as they see these issues, they're trying to patch it up, if you will. Right?
Last question.
First of all, thanks very much for a brilliant presentation. To go back to your the reason that you gave to give this presentation was about the dilution of science and you know, how the hype is sort of contributing to that. How do you see that playing out, and what can we do to avoid the dilution of science?
I do not give answers here, right? So that's it's I'm just a grumpy old man just complaining here. Right?
Yeah.
What do we need to do? I'm not sure. Like, and that's the depressing truth here, right? So for the next 2 years at least, people are going to go crazy with this AI because everyone is demanding and it's coming from the top as well, right? Like everyone is demanding more and more AI, and it's not enough. I feel like people are forgetting about what customers are really wanting, and it's just trying to shove AI when it's not even needed, right? So, do we get back to the basics and just do things? But I mean, that on itself is a risk as well. So it's I don't blame them, right? Like it's again, I offer no I offer no answers, only more questions.
Can you all please join me in thanking Sachin